Okay, so let's go ahead and take a look at this next lesson. So we're going to do some related rate problems, and we're going to do some maximizing or minimizing volume problems in this lesson. So example 1, water in a tank in the shape of an inverted cone. The height of the cone is 10 meters, and then the diameter is 8, as shown in the figure below. Water is being pumped into the tank at a rate of 2 meters cubed per minute. How fast is the water rising when the water is 5 meters deep? Okay, so easiest thing to do, in my opinion, is to go through and label all my variables. So we'll set that let V be the volume of the water in the tank. And then we let H be the height. Of the water at T minutes. And then we'll let R be the radius of the surface of the water at T minutes. And then we're also given that dV dt is equal to 2 meters cubed per minute. The height is 10 meters. The diameter is 8 meters, so that means that the radius is 4 meters. And I want to figure out dH dt when H is equal to 5. So we know that volume is equal to 1/3 pi r cubed H for the cone. Okay, but we have R and we have, I'm sorry, not pi r cubed, it's pi r squared H. Well, we have like two variables, so we can't really take the derivative implicitly yet. We're going to need to eliminate one of these variables first. So I have like this similar triangle situation where my entire height of my cone is 10. I have a little h, I have a little r, and then my radius is 4 because my diameter was 8. So we know back from similar triangles in a geometry unit that 4 divided by 10 is the same thing as r over h, because we can do that similar triangle relationship, which means, so 4h is equal to 10r by cross multiplication. So then r is equal to 2h divided by 5. So now I can take this and substitute it in, substitute it in for r here. So my v is equal to 1/3 pi 2h over 5 squared times h. So now v is equal to 1/3 pi 4h squared over 25 times h. So v is equal to 4 over 75 pi and h cubed. Okay, so now I'm going to take my derivative implicitly. So dv dt is equal to 4 over 75 pi and then 3h squared and dH dt. Okay, so my dV dt is equal to 2, so 2 is equal to 4 over 75 pi, and then 3, my height is 5 squared, and then dH dt. And now all I have to do is just isolate dH dt. So 2 is equal to 4 pi dH dt after I simplify this, because 3 times 25 is 75. So now I'll divide both sides by 4 pi, so I get dH dt is equal to 1 over 2 pi meters per minute. Okay? So now let's take a look at our next example. Our next example is going to use some similar triangles as well. Let the light on the ground 100 feet away from the building, shining at a 6-foot-tall man walking away from the street light and towards the building at a rate of 4 feet per second. How fast is the shadow on the building becoming shorter when he is 40 feet away from the building? So let's do some things with the variables. So let S be the height of the man's shadow. Let X be the distance between the man and the light. Oops, not M. And then let T be the time in seconds. We are given dx dt, not dv dt, sorry, dx dt is equal to 4 feet per second. The man is 6 feet tall. Distance between light and building is equal to 100 feet. And I want to find ds dt at x is equal to 60. Okay, so I'm going to set up the equation using similar triangles. So what I have is I have kind of this situation where I have x here, I have 6 here, I have s there, and then this entire thing is 100. So what I could say is 6 over s is equal to x over 100. So s is equal to 600 over x, which makes s equal to 600 x to the negative first power. So I could take the derivative implicitly. So ds dt is equal to negative 600 x to the negative second power times dx dt. And then I can just plug everything in. So ds dt is equal to negative 600 over x squared dx dt. And then my x is equal to 60. So ds dt is equal to negative 600 divided by 60 squared times my dx dt, which is 4. So after you simplify, ds dt is equal to negative 2/3 feet per second. Okay, so now let's do one of the most commonly missed related rate problems, which is whenever we have to find the rate of change of theta, it always gets a little tricky. So a camera on the ground is 200 meters away from the hot air balloon and records the balloon rising in the sky at a rate 10 meters per second. How fast is the camera's angle of elevation changing when the balloon is 100 meters in the air? So what I'm looking for is d theta dt. We always use tangent. So let's call this other side z. So tangent of theta is equal to opposite, which is x over z. And then I take the derivative implicitly. So secant squared theta d theta dt is equal to quotient rule. So low d high minus high d low over low squared. And then this is a fixed 200 meters, so dz dt is equal to 0. So secant squared theta d theta dt is equal to z dx dt minus 0, all divided by z squared. Okay? So now what I'm going to do is I'm going to try to figure out any other values I possibly might need. So I'm looking at, I need to figure out, I have what z is, but I'm going to need to figure out secant of theta, which secant of theta, so here's theta, so secant is going to be my y divided by z. Okay, and I know that x is 150 feet, or 150 meters in the air. So that means that using Pythagorean theorem, 200 squared plus 150 squared is equal to y squared So by simplifying this, we get y is 250 meters. So that means that this is 250. So secant of theta, and I'm going to square it. So secant would have been, instead of adjacent over hypotenuse, it's hypotenuse over adjacent. So that's 250 divided by 200. And then d theta dt is equal to z, which is 200. My dx dt is equal to 10. My z squared is 200 squared. And then I can start simplifying some things. So my 200 and my squared cancel out. My zeros cancel out. Everything's divisible by 5, so that gives me 5 over 4. So this is 25 over 16 d theta dt is equal to 10 over 200, which I can reduce again. So I get 25 over 16 d theta dt is equal to 1 over 20. And then I need to invert and multiply. So d theta dt is equal to 1 over 20 times 16 over 25. So they're both divisible by 4, so that gives me 5 and 4. So d theta dt is equal to 4 over 125, and this is radians per second. So now we're going to talk about max and min problems. So when we're trying to maximize or minimize problems, remember we have primary equations and we have secondary equations. And then the secondary equation's purpose in life is to eliminate one of the variables in my primary equation so that I can take the derivative, find critical numbers. Hopefully I don't have to use the first derivative or second derivative test to tell whether or not I have a min or a max. Hopefully there's just one critical number. And then we go ahead and we solve the equation. So, example 4. The graph of y equals negative 1/2 x plus 2 encloses the region with the x-axis and the y-axis in the first quadrant. A rectangle enclosed in the region has a vertex at the origin and opposite vertex of the graph. Find the dimensions of the rectangle so that the area is a maximum. So I would start by drawing a graph. So here's 2, down 1, over 2, down 1, over 2. So my graph looks something like this. And what I'm trying to do is I'm trying to make a little rectangle. One of the vertices is at the origin. It's something like this maybe. So the area of that rectangle is a maximum. Okay. So in this point we'll just call it x comma y. Okay. So the area of this rectangle is some distance x and some height y. And I want this to be a maximum, which means that that's the equation I'm going to take the derivative of. Now I know a secondary equation. This is called my primary because it's what I'm either maximizing or minimizing. My secondary equation is what I'm given. So this is my secondary equation. And I'm going to take my secondary equation and I'm going to plug it in for one of the variables. So I get area is equal to x times negative 1/2 x plus 2. And I'm going to distribute. So negative 1/2 x squared plus 2x. And then because I'm maximizing area, I need to take the derivative. So a prime is equal to negative x plus 2. And I'm going to set this equal to 0. So x is equal to 2. Because I only have one value, I don't actually have to test to see whether or not it's a maximum or a minimum. But I could if I wanted to. I could use a second derivative test. And when I take my second derivative, I get negative 1. Negative 1 is less than 0, which means that the function is concave down, which means that at x equals 2 is a maximum. So now, if at x equals 2 is a maximum, I want to find the dimensions of the rectangle. So if x is equal to 2, I need to figure out what y is equal to. So when x is equal to 2, my y is equal to negative 1/2 times 2 plus 2. So y equals negative 1 plus 2, so y is equal to 1. So the dimensions of the rectangle, the length is 2, and it doesn't give any units. And the height is 1. Okay? So now, we have our next example. Open box made using a square sheet of tin. So to make an open box, I actually have to cut some sides out. And so 20 inches by 20 inches, cutting a square from each corner, folding the sides up, find the length of the side of the square being cut so the box has a maximum volume. So we're going to let these be x. So then that means that this distance here is 20 minus 2x. So then the volume of this is length times width, so 20 minus 2x. And then times the height, which is x, because I'm folding up those corners and it's a side length of x. And now I need to take the derivative of this. So I can do this a couple of ways. I could do this using product rule. So I could have done v is equal to 20 minus 2x squared times x. And then I could have done product rule, which would have been, so dv dt, or dv dx in this case, is equal to second times the derivative of the first, which is 2 times 20 minus 2x to the first power times negative 2, plus the first, which is 20 minus 2x, times the derivative of x, which is 1. And then I can factor out by grouping. So dv dx is equal to, I can factor out a 20 minus 2x, and I'm left with, in my first term, negative 4x, and my second term would be plus 1. Oh, wait, this should be squared. Sorry, not plus 1. Plus (20 minus 2x). Okay, so dv dx is equal to 20 minus 2x, and then this would have given me make sure I'm doing this right. Negative 4x, so negative 6x plus 20. And then you can factor out something in common out of both of these, or you're just going to set this dv dx equal to 0. So 0 is equal to 20 minus 2x and negative 6x plus 20. So my first one, when I set my 20 minus 2x equal to 0, I get x is equal to 2x is equal to 20, so x is equal to 10. And the negative 6x plus 20 is equal to 0, so 6x is equal to 20, so x is equal to 10/3. And now I could use the second derivative test or the first derivative test, but one thing that you should note is that if I were to take x equals 10 and plug it back into my original equation, this would have given me a volume equal to 0. So x equals 10 actually does not work. So I could use the second derivative test to see whether or not x equals 10/3 works or not. It's okay for you to proceed without testing it as long as it doesn't ask you to justify your answer. So I would have just gone ahead and said that x is equal to 10/3. So that means that the side of the square that should be cut or the length of the side of the square that should be cut is 10/3 inches long. Okay? And that is it for this lesson.